Okay, so we'll continue today with where we stopped last time first. Uh, um, First start with where we stopped last time, which is the slides from the class. Let me just move and show the class website. All right, I'm sharing the screen. Okay. Yeah. Okay, so what we have here is a new assignment. I mean, kind of the updates that we have today. And we'll talk about the previous assignment as well, maybe in the second part of the class. If anybody has any questions or would like to demonstrate anything. I know that some people are still submitting, so we can kind of talk about this in general, maybe not publish any specific solutions, but we have the second assignment here with a submission as usual on Canvas. So it's going to be like a transition from talking about Tonnetz and tonal spaces to algorithmic composition, if you wish, with the example of Mozart dice game that has a probability aspect to it. So kind of as a motivation or as a further study of Tonnetz, we go to lecture slides. Yes, so this was where we ended last time. We spoke about Tonnetz spaces as a way to represent aspects of music theory, of Western music theory, and namely the idea that after we spoke about consonant and dissonant intervals for consonants and dissonance as a phenomena, perceptual phenomena, and that gives more weight to relations of fifth, third, minor, and major. Using these kind of more important intervals, if you may call it this way, we get to the point of having a representation that puts notes on this sort of a lattice where distances along one of the axes, so these triangles are arranged in a way that you have, in this case, the way it's oriented is that on the horizontal axis, you have notes that are spaced fifth apart. And again, I mean, we're using this musical terminology that I hope everybody's comfortable with. A fifth means going from C to G, from G to D, D to A. This is so-called circle of fifth. And it's counted by going 5 white keys from C to G, and then going 5 keys up from G to, so from C to G, from G to D, it's another 5 white keys, but then you fold the D back. So this is where you kind of looking only at the names of the pitches, and same thing going down from C to F. But then at a certain point, we start hitting the black keys, the sharps, or the flats. Again, for those who are not 100% comfortable with musical notation and figuring yourself out like around the musical keyboard, I think the best way is really kind of to sit next to the piano and try to see how this counts. Basically, a fifth, as we call a fifth, means, as I said, 5 white keys But if you go on half steps, black and white keys, I don't have a keyboard here. I can bring it up, but I'll just kind of move on unless people have questions. So this will be 6 steps, 6 semitones. Okay. So this 6 semitones is the arrangement of the fifth. Then you have a minor third on the right diagonal, or like the diagonal inclined to the right, and then you have a major third on the left diagonal, and yeah, and that's basically an emphasis on these triad relations. That the way they're arranged, you have minor chords, minor triads, so any 3 notes arranged in this way are a triad, and you have these minor, major triads, and you have relations of parallel keys, relative keys, and again, these are very musical concepts, and these musical concepts basically claim that in Western music theory, because of the preference of these 3 intervals, and then structuring, so the whole idea here is really giving, trying to explain harmony. Okay, it's not about sequences of notes, it's about parallel arrangements of notes, so notes that play together. So with this arrangement, you basically think that, you know, looking at positioning of notes makes sense as if we are looking at things on this torus, and this is a justification or explanation, motivation for the Tonnetz features that take chroma vectors and represent them as Tonnetz features by creating this transformation matrix, and you multiply your chroma vector by this transformation matrix. That gives you a 6-dimensional vector phi, and then you know, you multiply chroma by this matrix to get from 12-dimensional representation of a chroma to 6-dimensional representation of these tonal relations, or the Tonnetz transform. And then you calculate distances, Euclidean distances between chromograms. So well, let me kind of jump back to homework before we, okay, so yeah, please check out these things. There's this demonstration of chroma representation that is also used as an interface, also as a way to analyze music in this application. And we stopped here, which is actually an article that I think is interesting and valuable for where we stand at this point, that will combine the idea of these spaces, or what they call neo-Riemannian spaces, as a way to compose music. But before continuing with the topic, let me kind of show the homework and maybe answer questions if you have. So let's go again to the assignment. Okay. Yeah, so this is, let's see. Yeah, it will open to Google. Okay, so as usual, or as we did last time, that's kind of the format that we are, no, sorry, not the Media Audio Lab, that's the previous one. This one is a dice game. Okay. And there are instructions here, and an extra zip file with Mozart dice game musical, basically musical clips. Okay, so let me kind of try to explain here what is going on. I don't think I can actually open the zip file on the drive, right? It will not. Okay, well, can I look? Yes, so What we have here is a directory that you will need to download and use it in the notebook that has a lot of MIDI clips. Okay, so you can see there all these numbers 01, 02, so on. We have all of these file names that we refer to in this notebook. Okay, so each number here is one of the MIDI sound files. Okay, for some reason I don't know why the let me just make a quick check, because then I can download this and open this again on my computer, although I do have a local copy where I prepared homework, and just to make sure that we are all correct. Just 1 second. So I want to okay. So I downloaded this Mozart dice game. Let me open it. Yeah, I don't know why. Yeah, when I was browsing this on okay, yeah. So these are the MIDI files, and if we go back and look at the Mozart dice game, okay. So here are the different names that all should have these three, yeah, CDA and the 3 digits, 3 numbers that represent the MIDI clip. So if we open one of them, you can see that they are basically short musical excerpts. Okay, this is like, and they all have the same number of bars. They all have basically not bars. It's kind of a single bar, actually half a bar. It's 2 quarters. Okay, for some reason the MuseScore opens this in a way that the left hand of the F clef is on top, but it doesn't really matter. So this is one clip, this is another clip, this is another one. So you can kind of see where we go from here. We basically have these little half a measure musical pieces, okay, that each one of them has a name, or the name is basically the CDA and a number. So we downloaded this from one of the web scrape, one of the web demonstrations of Mozart dice game that claimed they entered the notes from the original Mozart dice game book. So what is the Mozart dice game? You can look it up and either find some existing web applications or a lot of explanations exist on the web. The idea is that during Mozart days, and he wasn't the only one who practiced this method, people used to publish these dice games or compositions where you had a booklet with these kinds of measures written down and the table, okay? And that table represented the bars, okay, and the possible options for recopying one of these segments into the first bar, the second bar, the third, and so on. So you had these 8 bars and these 8 bars, actually half bars. So you have the A and the B. So these measures are the options for A1. These musical excerpts or files are options for measure A2 and so on, A3. So this is your eventual list of measures that comprises the composition. So by random choice of one of these measures, you have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Why 11 and why it's a dice game? Because if you throw 2 dice, you have numbers from 2 to 12. Okay, in this case, so you have basically 11 choices. In our case, we're not throwing a dice literally. So our choices will be, instead of going from 2 to 12, we go from 0 to 10. Okay, but we still have 11 choices. So every bar we make one of these choices. So how do we actually realize the Mozart dice game? What we do is we choose, and so I provide kind of part of the code. You place your Mozart dice game somewhere in the directory. So you'll have to change maybe the prefix as you wish. And then you have the list of measures, right? And then from this list of measures, so every A here is basically a string, okay? So what you have to do is, from this list of measures, okay, you take one of the bars, okay? So you read A1, A2, A3, that's kind of a regular for statement, the loop, okay? And then once you read every one of these bars, you split it, split the string. This is where the bar list split works. You get basically a sequence of these numbers, okay? And then what you want to do is choose one of the random bars from the list of measures. So basically what you have is, here you'll have this as an array, okay? And you have to choose by using the random library. So you can kind of look up, do help on random, and find a way. And we'll actually talk about random later on in the class. You choose one of these, okay? So depending on which bar you are, okay, or which measure you are, okay? So in A1, you'll choose one of these numbers. In A2, you'll choose one of these numbers, basically by selecting entry in this bar list, okay? And the idea is that you sequence them, okay? And create a path through this matrix, going from A1 to B8, where you each time select one of the random bars. Okay, so that's kind of the whole idea. Kind of now it's a long explanation for something which is kind of straightforward. We have basically combinatorial number of possible compositions here, and you can calculate how many compositions there are. So you have 11 options at every step, and you have 16 steps. So you have 11 to the power of 16 possible compositions encoded in this database, okay? So what you'll do is make that sequence of selected bars. You'll, by just putting this in the path, using the prefix and the suffix with this random bar, you point to the right file. And here what you have to do is either using music MIDI or converter parts. They're all Music 21 existing commands. you open this musical segment, basically read MIDI file of a new bar from path and append it to Mozart stream. Okay, so what is Mozart stream? So this is the structure. So in this homework, you'll have kind of to a little bit dive more deeply into the Mus270C structure. So stream is one of the basic concepts of or building blocks of Mus270C. So this is how you initialize it, okay? And then you can easily, hopefully, by searching either examples or documentation, to see how you open a MIDI file in Mus270C, and it opens as a music stream. Okay, so you create a stream, you read the MIDI file into that stream, and then you can parse same way as not parse, you can append same way as this is just selected bars here, which is, I think there should be here, maybe it needs to be initialized as an empty string. Same way that you append list one to the other, you also append streams to create a new stream. So here, really the whole thing is just random selection. With this random bar, you find the file that you're looking for. The selected bars is really for you to keep track of how you sequence your bars. It actually doesn't have to be used anywhere else in the homework, but this code here opens a MIDI file as a stream and concatenates every time the next measure to the final stream, and then you write that Mozart stream. Okay, so we initialize the stream here, and here you will open and append it, and eventually you write the Mozart stream into a file, Mozart dice game. Okay, so this is the first part of the homework, Mozart dice game implementation. Nothing more really than some random selection, using append on streams and writing it down. So let me show you, this is one of the possible results of such running this code. So we saw the individual bars, and then after you run the code, you basically get your 16 bars of the Mozart dice game. Let me see if I can play it. So, okay, let me see if I can. I probably would need. Yeah, I'm not sure. Okay, I'll play it. Let me know if you hear it. Okay, and now the question is, how can I see you? 1 second. Where's my audience view? Okay, I don't see that little bar. So just speak up and tell me if. Okay, I think because it was the video. Yeah, so just give me a thumbs up if you heard it. So as I said, like every time you run it, you'll get a new composition. Okay, because it will basically concatenate every time a different bar or a different measure from these listed measures. I'm kind of using the measure and bar here in interchangeable way. The way MuseScore opens it up, it kind of basically takes two measures and puts them into, and the measure and the bar is usually the same term. So the way it makes the notation here, it assumes four quarters as the meter, which means you have again, quarter is this note with the one stem. So 1, 2, 3, 4. So it basically combines two of these measures into one bar. So the measures we refer to the original dice game composition. This is really more of a notational thing that Mus270C does. So in fact, what you have is if you count by bar lines here, you have eight of them, but basically you have 16 because each one is recopied into one. So if you look at 2 quarters as a measure, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And this is how it sounds, okay? Okay, just quick thumbs up. Could you hear it?
We can hear it.
Can?
No.
Okay, no. You could not.
Could not.
Could not. Okay.
Yes.
So that's the problem. I think I have to restart Mus270C every time. Okay, let me see. Yeah, I'll have to find where that Mozart dice game is if I reopen it, but
Or can you try setting the output of music? I don't know the sound of music chord to the Zoom. You
no,
know,
I
Zoom
did.
has a yeah.
Right, no, I did that. Yeah.
Oh, that should work.
Yeah.
Yeah.
So I think I have to close and open for some reason. I mean, I can try
Okay.
again. I am sharing. Sorry. I am sharing audio, sharing sound. Yeah, I had it last time. For some reason, I don't know if there is a way kind of to reset without quitting. So let me restart it. Okay, and let me find quickly. Okay, one more second. It might not be exactly the same example. I'm just looking for one of these examples that is running, just to make sure that everything works in the assignments. So where would that be? Okay, well, I had it in the same folder. Let me see if it works now. Okay, that's the same. Okay, let's hope it works. 1, 2, 3. Okay, here we go. Okay, works. Okay, great. So you could hear it. So yeah, so the first part of the assignment will be basically generating or writing a small code that uses that data set, that collection of single measures or half bars, sequencing them into the musical piece. Now, I think the concept itself, I think, is more interesting than the actual technique. But the technique shows, at least, or demonstrates the ability to create maybe not infinite, but combinatorially large amount of compositions if you do have building blocks that are designed in a very specific way. Okay, so the idea of using randomness on top of a specific set of sound contents or MIDI contents, and being able to sequence them in the right way, actually shows that a lot of mechanical music composition is possible. And then, in some sense, this idea of querying a data set, and from that data set having some sort of a random process that drives the lookup table, at least very superficially, you can think about this as taking noise, turning this into music. And in this case, the noise is really random selection and pointing into that list. Or if you kind of want to make this, I don't know if this is mental leap or analogy that is in some sense a little kind of abstract. But if you think today about transformers, the query and the key and the value, there is this kind of analogy to database lookup, where you, well, in this case, instead of using a random input, you use the previous bar, or you use maybe use a noise that triggers a representation that then looks up something from this transformer structure, and the whole representation is looking up or having a query into the data set. So, and that use of terms of key query and value could be applied here as well, though. I mean, this has nothing to do with the transformer and the neural network that is the basis for GPTs. But I think there is this common idea of look up into a representation, and that lookup comes from some other process, some random lookup or some noise that drives the process, and that noise every time generates something new. So turning noise into structure by going through some sort of a either distributed representation as a neural network that takes noise into music, or actually looking it up in a very big data set, or looking it up in a recording and doing concatenative synthesis, at least on the level of randomness that allows exponential number of possibilities, and that random process actually every time finds something in another representation to create music. Frankly, happens in neural networks in generative models a lot. So yeah, so I think it's kind of interesting to figure out that you could at least find a way by carefully or manually preparing a data set and throwing dice, make a lot of novel compositions. And later on, when we talk about machine learning, you can think about sort of that parallel task where instead of having a manually prepared data set, maybe you can learn this table. Maybe you can kind of go and find a way from a big data set to create a database that you can look up and sequence in new ways to create more and more musical examples. There's not much control here, except for that, every time you randomly choose call your random function here, or throw the dice, you create a new composition. And it would be much more interesting to see if the choices could be specified by providing either some textual input, or providing another musical example, providing some sort of a prompt, So you see where I'm headed with this. I mean, basically kind of a little bit building on this very naive example as a motivation to much later machine learning driven compositional algorithms. Okay, so I think enough said about this. So what will be the next? The next part actually brings us back to Tonnetz. Okay, so in the Tonnetz analysis, we'll be using a second library, which is pretty MIDI. And by the way, I think so here we used Music21 stream. Actually, we don't need the copy here. We're not doing any deep copies, but that's the first part. And the second part, we are using another MIDI package called Pretty MIDI, just because it's much easier to handle some aspects of music by thinking about this as a piano roll. So it's talk about piano roll. So in the second part of the analysis or the assignment, we do the Tonnetz analysis, where we open that Mozart dice game with Pretty MIDI. And you did that also in the previous homework. We displayed this as a piano roll. And your assignment here is actually eventually to go and create a Tonnetz matrix and to get the Tonnetz vector or Tonnetz representation, we first go through the chroma matrix. So what is chroma matrix? The idea is that you cut or chunk the piano roll into slightly larger chunks. So you have these beats. How many beats? It's your choice. Okay. So instead of, again, I kind of give a quick reminder of how the Pretty MIDI works. So the piano roll, you have some sampling rate. Actually, you can use much higher numbers here to get much more detailed representation of your music. Okay, so this is the this little minuet that we generated before. Now each column here basically represents maybe some portion of a note, and you have many columns that actually go through the MIDI ticks and recreate the piece that we had before. Now you want to turn this into chroma, and this time it's a MIDI chroma. Okay, so we kind of use interchangeably the concept of chroma. There is a chroma that can be derived from spectrogram, from analysis of audio, and there's also chroma that could be applied to music notation, symbolic music. Actually, it's much simpler concept if you think about notes. This is called pitch class. So in this case, chroma is really just the name of the note without referring to which octave it lies in. Okay, so if you think that 60 is a middle C, is 60, the MIDI number 60 is middle C. So all you care about is that this is a C, and same way it will be 72 and same 48. Okay, so all of these notes, we don't care what octaves they are pitch class 0. Okay, so what you do is you have 12 pitch classes. Okay, so the whole idea is basically to cut out the chunk of this piano roll and create a chroma matrix that sums the piano roll at 12 pitch classes over some subset of columns, which we call beat num. Okay, so you can play around whether you want to take 8 of the slices of the piano roll or more and aggregate them into basically a 12-dimensional vector that contains the number of notes or the number of occurrences of notes in every pitch class. Okay, so if you have any questions, kind of let me know. But this is basically the main part of this assignment, kind of turning this into something like this. Okay, so what you can see is that we basically aggregated these notes. So you can see that this was 500. This is much less. Okay, so 500 something. This is 60 something. And these are the 12 notes. And these 12 notes are basically summary of the notes that appear here, and so on. Okay, so these are the chroma representations. And then we go to the Tonnetz part. And here you have to complete the missing lines from the Tonnetz matrix. So let's go back to the slides about Tonnetz. You basically have these. This is the Tonnetz transformation. This is the matrix. So you can see that this is R1 sine of L 7 pi divided by 6, and L goes from 0 to 11. Okay, so I kind of provide the first. Okay, just have to look twice. Yeah. So where we? Yeah, so we're here. So you can see this is the first line, the fifth X. Okay. Okay, this is the X. Okay, so this is the R1. Okay. R of the fifth. So we have R1, R2, and R3. The R that corresponds to the fifth. Okay. The R that corresponds to the minor thirds, and the R that corresponds to the major thirds. So in the original paper, if you remember, we looked up last time, and they use 1, sorry, for the fifth. They use 1 for the minor thirds, and they use 1/2 for the major thirds. Why they do the scaling? We just use that paper's suggestion. There isn't really a very deep justification why this is the correct one, but it kind of scales these 6 parameters. So you have fifth X, fifth Y, minor third X, minor third Y. Again, fifth X is here. That's the X, and this is the Y. Okay, so every chroma here, this will be R1 sine, and this, the pi 6, 7 pi divided by 7/6 of a pi. Okay, this is the angle going around the circle. Okay, why? Because we have basically 12 nodes. Okay, and these 12 nodes divide. So this is 2 pi. 2 pi divided by 12 is the same thing as pi divided by 6. So every step here is 6, and then you go from 0 all the way to 0, and then 7 pi should land us in the neck. Okay, is that you kind of see that I'm explaining this correctly, and everybody sees that. Okay, so every shift in an angle here is 7/6 of a pi, right? Or if you use your 12, so it's the 14. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So 10, 11, 12. We have 12 steps. So when we multiply this by 0, we are here. Okay, and this angle, if we go all the way to 11, we have 11 pi divided by 6. We should be here. So the 12th one, okay, will be 12 divided by 6. Just a second. So L is multiplying, right? I don't know why I'm a little confused. Why this is 7 pi divided by 6, right? That's the number here. Yeah, 7 pi divided by 6. So the chroma itself, okay, is a number from 0 to 11. Okay, so it'll be sine of 7 pi divided by 6 times 0. So it goes from 0 to 7 pi sinus of 7 pi divided by 6, 2 times sine, 3 times all the way to 11 times sine. And why I'm having difficulties Seeing that. Okay, I know I'm kind of, for some reason, blanking out on something that should be evident, that this is the correct way to go around this circle. And I'm just kind of confused why, if we get to from 0 to 11, if you go to 12, 12 divided by 6 is 2, it's 14 pi. 14 pi should be, sine 40 pi should be again 0, right? So we go here, 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 and go to 0 there. Like, I think that's correct. I mean, please check the geometry, okay? That really should be kind of straightforward. So this is the sine aspect, this is the x, okay? This is the y, okay, the second one. This is the x and the y, the R2 for the minor thirds, and this is the x and the y. Okay, this is the position, x and y. Anyway, what you have to do here is basically in a way which is analogous to this line, just complete all the rest. So we kind of try to do together the first line, so it will be R5, and here will be just second line will be cosine, the same expression, but then the major third would be with, sorry, the minor third would be with R minor third, and you just recopy the right equations here. So it's the sine of 3 pi over 6. So you know, go back and forth between this slide and this assignment and just complete this matrix. Okay. So now what we get is we get these 6 coordinates, x and y. And once you have this Tonnetz matrix, okay, we use this to make the transformation. Okay, Tonnetz matrix times chroma. That's exactly this multiplication here that we do. And it's also normalized by the chroma itself. So I provided the Tonnetz function. And then we have the distance. And the distance basically tells you that you want to measure distance between 2 chroma vectors, okay? Or sorry, between, well, we already translated or transformed the chroma vectors into Tonnetz vectors. So the distance between these Tonnetz vectors is really just a norm, okay? And you can call the NumPy lean alg norm function. To calculate this, you can, of course, do the Euclidean norm yourself here. But, it's just the normal vector distance in a two-dimensional, sorry, in 6-dimensional space. So it's Euclidean distance between these A's and B's. So A and B, here it's basically a little less comprehension that you basically read these. So this is kind of, for those who are new to Python, just kind of, instead of a for loop, you can write this in an iterator. So it's kind of an iterator here that reads A and B, calls each one into Tonnetz, and that gives you the A Tonnetz and the B Tonnetz, and then you calculate the distance. All right, so I kind of going very slowly through this notebook, just for the sake of also having a little bit more dive into Python for those who are not 100% fluent in all of these languages. Okay, so here we have that. And what we want to do is really use the Tonnetz distance and analyze your dice game composition. So of course, every time you run the first part of the code, if you've finished the whole notebook, you'll get slightly different analysis here. And what we want to do is basically calculate 2 things. One is how, we call it chord change, but basically this is kind of the Tonnetz distance, okay, from from start to end in 2 ways. One is every time relative to the first beat or the first segment, first Tonnetz vector. So depending on your resolution, you can get, so, if you take a very large chroma vector, let's say you take every measure, then you'll have 16 points. You can cut it into shorter segments, okay? So if we go back to the music representation, it really depends, what you calculate chroma. If you take a quarter note, you'll basically sum all of these notes and you'll have a chroma vector. This will be chroma vector. This will be chroma vector. This will be chroma vector. And as you can see, some of the chroma vectors will not be really, you kind of lump them or you kind of like straighten them all together and you think about all of these notes. If you think about this as a chord playing simultaneously, it's actually not a meaningful chord, right? It's like what they call cluster. But in many cases, this is a meaningful chroma vector. So even that this notion of chroma that then becomes a Tonnetz is a little ambiguous or problematic for music analysis because it kind of aggregates instead of bag of chords, it kind of takes a bag of pitches and puts them in the 6-dimensional space. But if this was a melodic line and you think about this as a chord, that's not really a meaningful chord. So I guess this bar will throw you out of anything close to any chord. But you can kind of try to see if you do approximate these things into chords, how this thing progresses. Now, if you aggregate 2 quarter notes into chroma vector, maybe you'll have more weight to the C major. This is the C major chord. With these notes kind of being embellishments or some added notes, but they will be weighted less than these notes because in the piano roll, that C will be repeated 4 times here and 5 times out. And so it'll be 5 to 1. Let's say this D, which appears once relative to C and G and E that have much more weight. So taking larger chunks probably will kind of compensate a little bit on the problem that you use chroma here also to analyze melodies. And here, that's going to be pretty tricky because, you have all of these notes running. So the C kind of is held at least for 1 quarter. So you'll have more weight for the C. You do have a G that repeats itself, but you have all these other notes that also kind of repeat a lot. So this is why chroma is a little bit of a difficult concept to apply to capture, the melody, but it does capture the dominant harmonies, okay? So you should be able kind of to see something that kind of relates to C major here, maybe less to C major here, but maybe not too far. For those who are a little bit more fluent in music theory, you can see that this is something based on a G chord, okay? Although this G7th because you have an F here. So the notes of G are here, and then it goes back to C. Okay, so you have basically C, C, G, C, and then you have a D major here, okay, with the F sharp. Those who are not like into music chords and theory, and this didn't say much, just think about these as aggregates. So in this case, you'll have really the D here as the root of the chord. You have the 3rd here, the major 3rd and the 5th, D, F sharp, and A. So you aggregate them. This is, inverted. That's basically it's a 3rd inversion of 7th chord here. This C is basically kind of the 7th of D. For those who are kind of following in music theory, so it's still a D chord 7th with an inversion, but if you aggregate them together, you still see something that is closely related to the D major chord here, and you can kind of measure this in the Tonnetz space. So one of the analysis graphs will basically compare every, let's say, for the sake of the argument here, let's say you analyze chroma by every 2 quarters. So you'll basically be comparing chroma. You'll have that chroma as your anchor, as your baseline, and you compare the chroma of this to this one, chroma of this to this, this to this, and so on. So basically, you see how you move away from the first initial chord. Now, why we compare everything to the initial chord? Because in some sense, at least in a lot of tonal music, this establishes the tonality, that establishes the key, and the whole kind of scale or tonality. And again, I'm using musical concepts that you might be not that familiar with, but this whole piece is written in C major, right? So you'll see how you drift going from C to other keys, okay? Or other chords and then to other keys as well, because once you have the F sharp, you can think that this is actually, you move a key here, and then you kind of going back and forth, and you return to C. Okay, so that one trajectory is really starting from the first chord, how you move away and how you come back. And the second analysis is really differential in the sense that this relative to this, and then this relative to this, and this back to this, and so on. So you basically do measure by measure, or half a measure if you want, by half a measure comparison of the tonal changes. Now, one other thing, because you are going to play with the dimensions of your chroma vector, of course, you can take a chroma vector, which is very long. You can summarize all of that into chroma vector, okay? Basically, taking two of the original Mozart measures into one chroma vector. Here it will be maybe a good thing to do because it kind of eliminates the influence of the melodies. But here you already will be confusing yourself because you'll have a G and a C chord aggregated into one chroma vector. And so this brings a concept which is important in at least in tonal music, is kind of your so-called harmonic rhythm. Okay, so we didn't speak yet or talk yet too much about rhythms and representations of time and temporal patterns. That'll be probably next week. When we talk about Euclidean rhythms and some algorithms, how do you basically try to select, the rhythmic patterns, or how things repeat in time in terms of some kind of a. Here it's 4 quarters, so you kind of like basically have the constant beat, but you might have even these kind of da 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 da. That's a rhythm, but we'll use the concept of rhythm just to talk about kind of pace of events like the metronome. So here we talk about quarter note as the basic beat, and this is subdivided into 8 notes and 16 notes. But there is this concept of harmonic rhythm, which is basically how chords change. Okay, so you can see that here the C major chord basically stays for 4 quarters. Okay, so it has 1 and 2. Here we have the G chord that lasts for 2 quarters, and then again 2 quarters, and a C chord here, D chord for 2 quarters, going back to G chord. So we do a little bit of a harmony lesson here, but I think that's what makes musical algorithms, right? So you can see that your harmonic rhythm, okay, is about 2 quarters. Every 2 quarters, chord changes. Maybe it's held here for 2 quarters, and then a new chord for another 2 quarters, a new chord for another 2 quarters, and so on. Okay, so kind of giving away a little bit of what is the answer of setting up your beats, okay? But kind of given that guidance, just kind of set up your sampling rate for the piano roll in a certain way, and then kind of summarize your piano roll into beats, so it actually corresponds to nicely to kind of the natural rhythm of that piece, and the natural harmonic rhythm, okay? The changes of chords, how they happen, and create these two plots. That's in terms of the coding, and there is some discussion or some questions in the assignment text that I want to show. So here's your second assignment. Using the files in the folder provided with the assignment, complete the code to create a Mozart dice game, complete the chroma and Tonnetz functions, plot the Tonnetz distance relative to the first chroma vector, and changes between consecutive chroma, okay? Actually, it's consecutive Tonnetz. Okay, so I kind of like a little bit confused here, Tonnetz and chroma, but yeah, I mean, the vectors themselves become now Tonnetz vectors, not chroma vectors, okay? And to do so, you need to find a good, FS, the sampling in terms of the piano roll, and decide how many samples of the piano roll to assign to each chroma. So we talked about this. Submission, turning in the complete code. That's the usual. Submit the MIDI file of the Mozart dice game and the PDF. Basically, print the sheet music. And then this is more of that analysis. Describe qualitatively the difference between the two graphs. So basically, what I'm interested to see is, and can you kind of see what we talked about? Maybe you can have some jumps, which are not because the chords changes, but because of the melody that kind of threw the chroma out of something reasonable in terms of tonality. But then also you can have kind of a progression of chords that is shown by one of the graphs, or how far you go from the basic, the initial anchor, or the initial starting point, which is the first chroma vector. That's your tonality, how you go out and where you come back. And again, a little giveaways that, in tonal music, you usually come back to the same tonality at the end. So yeah, you can see that. You can try generating a few additional compositions. That's easy now. You can just, repeat the same and see if there is any kind of consistency, similarity in analysis of the different pieces. That's it. Now there is this optional extra credit. And there was a paper that uses the chroma using deep neural networks. We didn't cover that, but if somebody wants kind of to browse through that paper and explain what is the main idea, you can also find some musical examples of this paper. So if you want to do this reading, that's kind of outside of the 100% that you get, but I think that's kind of a possibility to keep aggregating a bit of extra points. So that's as far as the assignment goes. Any questions so far? Let's see if I can see the links. Okay, let me check the chat. All right, so, well, if everything is clear, I would appreciate kind of a thumbs up. Just kind of to know that, made sense yeah, yes.
I have a question. So for
Yes.
the last part of the assignment, do we need to calculate a difference of chroma for every measure, or just one?
So there are two of them. Yeah. So you run through the whole piece. Okay, you run through the whole piece. So your graph will be, as depending on what is your beat, what is the choice of a beat, which is I call beat basically aggregation of the piano roll slices into one chroma vector. So depending on how often you create the chroma vector, but let's say if you did this for every 2/4 of the original musical piece, okay, here you will have 6. So this is 1 and this is 2. You'll have 16 chroma vector or 16 Tonnetz vectors. So you'll have basically a graph that is 16 measures long, okay, 16 beats long, and you just have 2 of them. You have actually, if you think about differences, you'll have 15 differences. So if you calculate always the next one back to the first one, so you have 15 different steps, and if you calculate relative to the first one, you also have like 15. So it depends. You can repeat the first one twice, so you have 16 to 16. But yeah, it's whatever that number is. Let's say 16 by distance, and distance can be a number that represents these 6 chroma vectors within distance. Yeah. So I could show basically that graph in the solution, but I think it's pretty evident. It should be 2-dimensional. Again, 2 graphs, one on top of the other, and then you can just look and see if it makes not if it makes sense. What is the musical interpretation where this graph actually did capture the changes in the chords and that other effect of melodic movement that actually chroma doesn't really present. Okay. Yeah, so that's what it is. So what I propose is, yeah, sure. Thank you for asking. So what I propose, so our next thing is, I would like then to just to finish watching, or we didn't start really. I'd like to watch this video, which is a lecture about another use of chroma. It's not a deep neural network. It's more of these shallow methods that we'll get to that use create a kind of a network representation from chroma and use this for composition. So let's take what, like 10 minutes break and meet at let's say 10 minutes, so 3:20. Okay. We'll make kind of shorter breaks today, but maybe make 3 breaks instead of 2, because this is a video. I think it's about 15 minutes, but I don't want to drag you too much. So let's take 10 minutes break, and then we'll continue with this one, and then we'll talk about more about the randomness aspect of making some interesting random walk that can be used for composing. Okay, so I'll pause the recording. When I come back, just try to remind me. I'll try to remember, but if I don't record, then just remind me about that. And yeah, so we'll see you in 10 minutes. Thanks. Okay, so we're continuing with looking through the Tonnetz slides, the last slide, which is, sorry about the vibes. All right, so let's just watch this video, and then we can discuss this a little bit more before we kind of continue into really jumping into randomness and talking some basics of probability. So also have some theoretical aspects about probability plan for today, but let's look into this work, which I think is pretty interesting, and the authors use these methods. I mean, the composers / computer scientists. So I'll kind of talk maybe about there is a new opera coming up by one of the authors where he uses this also as a compositional tool. So let's just kind of watch the video. And yeah, I hope I share the sound. Everything should be fine, but if not, just kind of yeah, just burst in and tell me if anything doesn't work.
Welcome to this talk on random walks in Neo-Riemannian spaces, prepared by me, Dr. Phil Nguyen, and Dr. Eldad Sabari from the Faculty of Fine Arts at Concordia University in Montreal, Quebec, Canada. So random walks have been popularized in music since their inception by Jan Xenakis, for example. We can say that a trained ear can distinguish between a uniform distribution, a Gaussian, a Poisson distribution, Brownian motion, FVM processes, random rotations, etc. In this talk, we propose a new form of random walk steered by a transformation matrix representing a Neo-Riemannian space that can be learned offline or real-time from a corpus. So notes have become hard to choose. Tristan Murail in Spectra and Sprites, a famous paper, is known to have said that notes have effectively become very hard to choose for contemporary composers. By the time he made the statement, choosing notes had evolved from highly educated choices or mathematically oriented processes to total random choices. So it is well known that classical music chooses from the diatonic scale, post-romantic or Hollywoodian music from the chromatic scale in a somewhat neo-Romanian fashion. Atonal and serial music is chromatic in the sense of a 12-note scale, but but by now changes to the transformation rules occurred, such as the introduction of reversals, inversions, non-repetition, etc. By the time serial music had stormed the cultural elites in America and Europe, composers such as John Cage were experimenting with chance music and indeterminacy, while others such as Yanis Xenakis were building ways to generate arbitrary scales. He actually called them sieves. So Levy, in his thesis, distinguishes between purely algorithmic systems and composition systems from generative systems, which display a degree of learning and control. So a system that learns can be trained on a corpus of work and extract a database of patterns, whereas a system that displays control can function autonomously with minimal intervention. So generative systems have admittedly made use of a bunch of heuristics that come from computer science, such as cellular automata, artificial life concepts, swarm intelligence, or genetic algorithms. Generative systems have also been exploited in performance and improvisation to effectively serve as real-time accompaniment systems. So you have the Voyager system by Dannenberg and a bunch of other systems by Lewis, Tom, Young, Patchett, Carso, Mika. So generative systems in the literature, also there's a bunch of generative systems in the literature that make use of the Oracle factor algorithm. They were mostly based out of IRCAM, and they spawn a bunch of systems that are available in the Max environment, such as OMAX, DC2, or SOMAX. So on one hand we have generative systems, and on the other we have neo-Riemannian spaces. So there was a revival in the 90s and 2000s of harmonic transformational theories, such as those of Hugo Riemann, Weizmann, or in the 19th century. They were popularized by scholars such as David Levin, Fred Lerdahl, Richard Kahn, Dmitry Timashko, among others. So a basic pattern in those neo-Riemannian theories is that we embed harmony in a space equipped with a distance measure. So it's a very simple pattern, but it explains a lot. So here we have in A on your left a neo-Riemannian Tonnetz. So basically the transition graphs of major and minor triads. In the center we have the same thing but for the Weizmann space, so basically major, minor triads, and also augmented and diminished triads. So on your right, top right, is a random walk. Each axis is a note in the triad. So you see that the random walk actually clusters and then bifurcates towards another cluster. And at the bottom you have an open music patches to generate new Riemannian and Weizmann random walks. So chordal distance measures. Neo-Riemannian theories are based on the embedding of a set of possibly infinite chords into a distance space, which can be Riemann's original triangular matrix, a lattice of major and minor triads, Weizmann lattices, Lerdahl or true distance spaces, Timashko manifolds of all possible four chords, or some arbitrary Euclidean space or weighted graph, for instance, equipped with a shortest path distance, for example. There's a bunch of distance measures, chordal distance measures, which are listed in a survey paper by Rocher. So we have the Coster distance, the intervalley content, and the Estrada distance, the true distance, which is also called the spiral array distance, Lerdahl's tonal pitch space, and the Paiement distance. So here we have distance matrices computed on I think it's on a piece by Rachmaninoff using different distance measures. And the graph is actually a nearest neighbor graph, which was generated from the distance matrix. So on A, you have the true distance, so the spiral array distance, the chroma distance in B, Coster distance in C, and the Estrada distance in D. So you see that depending on the distance measure you use, things are pretty different. So the algorithm, the random walk algorithm, so it's based on a decay function, which is called delta t here, which is always equal between to something between 0 and 1. When it's 1, it's actually, it means that it's nothing's happening, and it's a distance matrix basically. So the smaller the number, the closer the chords. So in the algorithm here, in algorithm 1, we actually generate the distance matrix, the transformation matrix. On line 12 of algorithm 1, you see that there's two delta functions, so two decay functions. One for time, basically when the chords are further away in time, the decay function increases, and the shorter the time, the smaller the decay function. For the other decay function, it's actually decay function for the chordal value. So the harmony, we have a decay function for time and the decay function for harmony. And basically the closer the chords, the smaller the decay function. And the further the chords, the bigger the decay function. So algorithm 1 effectively generates a transformation matrix, which is basically a distance matrix. And algorithm 2, from that distance matrix, actually generates a random walk based on the data that was learned in the distance matrix. So here is what I'm talking about. We have an input query, so we start with a triad, for example. It doesn't have to be a triad, but here we have a triad. We select the fingerprint in the distance matrix. So basically each line of the distance matrix is equivalent to a chord. So for example, line 1 is C, line 2 is C sharp, etc., etc. And those fingerprints, we choose the input query, the fingerprint that is closest to input query, and from there we have a bunch of nearest neighbors in the distance matrix. Basically we choose the distance matrix, the fingerprint which is closest, which does not have a row that is equal to 1 completely. That means that the distance matrix actually has data for that particular fingerprint. And in the distance matrix, we have a bunch of k nearest neighbors. Here we have 3 nearest neighbors, and we choose the one in red. And then we go on. If we do a random walk, we just go on like that. We take the chord that was chosen, we choose some valid chord, and we continue. We generatively continue to choose notes. So here are examples of such random walks on near Riemannian learned spaces. So here's an example from Schoenberg. So actually this example, Schoenberg as Klavierstück is obviously atonal, so the generated music is actually atonal as well, and follows pretty well the genre of Schoenberg's Klavierstück. Here for Rachmaninoff's second concerto, piano concerto, movement 2, it didn't work out as well if we consider that something that works well is actually preserving the characteristic of the learned piece. Actually it generates something completely contemporary and atonal. It's probably because Rachmaninoff's piece is very neo-Riemannian, very chromatic. The succession of notes is very important in Rachmaninoff's piece. So So at the end there, you could hear some of the arpeggios of that second piano concerto. I know what piece it comes from, so I actually hear it. Here is actually another tonal piece that actually works pretty well, I think. It's very tonal. It's not as chromatic as Rachmaninoff's piece. It's very tonal. So properties of the pieces seem to have been preserved pretty well. So here it is. So here were the three examples. So let's conclude. This technique effectively represents a MIDI file in a neo-Riemannian space equipped with a distance. This representation, which can be a transformation matrix, like what I showed you, or a geometric embedding of the transformation matrix in Euclidean space, for example. This representation can effectively be used in deep learning techniques because it does not have the irregularities of a MIDI file. So one of the problems when you're using deep learning with MIDI is that MIDI is very irregular. So deep learning requires a very fixed length input. So we're going to talk more about this in a paper submitted for review, which was recently submitted for review. So concatenative and synthesis techniques and AI techniques can produce what we call here deconstructivist aesthetics. So more on deconstructivist aesthetics in music in a paper we recently submitted. So this term is actually very popular in architecture and philosophy, but has not stuck in music. So we feel that there's something very deconstructivist in the techniques that we were introducing. And you can hear it in examples that I gave. And finally, there's something we term reconstruction paradoxes, which occur in that deconstructivist aesthetics when using concatenative synthesis and AI techniques. Basically, the reconstituted whole does not always preserve the properties of the whole. So we're going to talk more about reconstruction paradoxes in a paper which was recently submitted for review. So thank you for your attention, and I'll take questions. Thank you.
Okay, so let me, before I exit the presentation, just kind of, okay, there is no easy way to scroll through the video unless I open this YouTube. But let me kind of maybe summarize or remind some ideas. What can
Welcome,
I? Just a second. Yeah, wait, we don't want to talk again. Let me just try to scroll it. Right. So, few of the concepts, right? Yeah, we'll talk a little bit about some history of and generative music, and the name of Jan Xenakis comes up. So some of these composers deserve special kind of notice or attention because they really pioneered the idea of using mathematical processes. So we'll talk a little bit about some of the generative stuff later on in class. We have few videos that we watched today. Now, I think the idea really that summarizes in one of the slides where he says that we make a random walk on a space of let's see, let me scroll the pages. We make a random walk on a space that is equipped with the distance measure, right? Yeah, this sentence, right? So the whole idea here is that, you know, that distance measure corresponds to a particular aspect of perception of difference, let's say. So what's the distance measure? Basically how similar things are, but they're not similar in any kind of physical sense. I mean, it's a perceptual distance, right? So we kind of like here make some kind of a mapping that two things are far apart because either in cultural sense or in perceptual sense, we perceive them as very different. And then it, of course, depends on what aspect of music you're measuring. And here it specifically says it's harmony. Okay, so there is harmonic distance, there is melodic distance, there could be temporal distances. So that also kind of that multidimensional aspect of music. And you know, the Tonnetz is just one of them. He mentioned also Weizmann spaces and other representations that basically take into account maybe more possible relations between intervals and claim that, you know, using these relations and you know, representing them as vectors. So one thing is that kind of geometry relations. If you represent something as a vector, then you assume that you can use dot products or Euclidean distances and norms to measure distances between these events. So now once you have that space set, then you actually create a trajectory. So create a piece, and in this case, you know, you actually, whatever that three-dimensional space is, that random walk is a composition. In this case, you know, it doesn't come back like what we saw in Mozart, with always returns to the same C major, but maybe this is something that needs to be, you know, forced as a condition. I mean, the whole question of, so composing is kind of represented here as a mathematical process of finding the right space and making some kind of a trajectory. Now that trajectory could be learned, and this is where he mentions Solmax and the factor oracle algorithms. Actually mentioned them before, where you kind of take musical example and you learn the transitions also. So there are basically two problems in trying to use compositional algorithms that also learn from examples, kind of machine learning. And this is that you have to find the right representation. And in that representation, you also have to sequence your units. So you need also to create the dynamic process. So we have the choices of the notes, but we also choices of succession of notes with time. So when we start talking about distributions of probabilities, we will have to kind of pay special attention to processes that actually are in time versus just choices of elements. Okay. In the Mozart dice game, the choices of time were predefined. You know, we had A1, A2, A3 to A8, and then B1 to B8. We actually knew how we have to sequence them, and the randomness was only in terms of choosing one of the options for A1 and one of the options for A2. If you open this up to a general problem, that becomes really this question of learning that graph, these transition matrices. So one kind of quick note about what these things represent. So usually these are kind of self-similarity matrices, if you wish, that take a musical piece, okay, so you have the time against time, and wherever it's black, that means that something that happens in this time is similar to everything that happens, you know, to all of these events. And we will probably go back and talk about these self-similarity matrices, but they kind of show the structure of the musical piece. So you can see that they're kind of blocks. This is kind of almost like it's not exactly correlation matrix, but very close to autocorrelation matrix for those who are familiar with this concept. Basically, it shows you say for every bar, I mean, if the time goes here from top to bottom, right? So you have this diagonal line, which means that everything here should be similar to itself. And then you can see that, you know, bar 1 is probably similar to all of these aspects, and bar 2 and 3 and so on. So you can see sometimes either blocks that repeat themselves or straight lines. I'm not kind of diving into the question of what it represents, but you can think about this also as a transition matrix, okay? And that there is a relation between graphs and transition matrices. Usually if you segment this and, you know, basically decide that only few of these nodes are black or white, so you decide which one connects to the other one. So we'll kind of cover this later on when we talk about either representing music transitions,
Piece by Rahman.
either representing music transitions as a Markov chain, where this is a transition matrix, okay? So that means that every bar or element that you have in the music can jump to one of the other elements, or you think about the graph. So if you're in one of the nodes, you can move to some of the connected nodes. So depending on the distance matrix, you actually see a very different aspect of similarity in music, and it's very hard to tell which one of them is correct. Okay, you can see that this graph is very kind of densely populated, has some interesting structures, and not just visually at least. This is maybe much simpler graph, but then the whole idea, if you learn these transition matrices from your data, then you can do a random walk on these graphs. Now, what does that random walk mean? Well, if your database is now created from an actual musical recording, and this is the whole idea of these SOMAX, OMAX algorithms that were shown. What was that? I think it was shown much earlier or later on. Yeah, so it's a little bit of a preview, okay, or spoiler preview, whatever, of later on, because SOMAX and OMAX are basically the base, you know, that kind of machine improvisation algorithms that we use a lot. And the idea is that given that you're somewhere in the musical piece, this becomes a query. So your query is where you are right now, and you look it up in the database, and that database is actually built from segments of that piece, of that corpus. And then you continue, you find possible continuations in this metrics, and you repeat this process over and over again. So we haven't still done anything like that in our homework so far, but you can see that it has these kind of relations to things that we've already been talking or touching. One is really, how do you do the query? How do you do the matching? Well, you need a distance measure if you want to think about this as a query. And then you need to construct a data set. And that data set is really either something that you prepare by hand or you analyze for music. And at least in the case of SOMAX and OMAX, we don't have any kind of neural network distributed representation. We actually use a corpus and we index the corpus. So these could be segments from the musical piece, and they're indexed by whatever the Tonnetz or whatever feature we extract. So you can think about this as metadata that labels, or these are the the keys. Okay, these are the keys for the database. So you match the query to a key to find this, the corresponding data point, which is the value. Okay, so I kind of almost repeat the concepts of key query and value that is really now so popular in transformers. But I mean, this here is done really in a much more like straightforward database query way, where you use the musical piece, whatever you generated right now, to look up into a database with this, the current segment in the musical piece, translated into a query that matches the key, and it extracts a value, and that value is the next musical piece that you're going to add, concatenate to your composition. And the whole idea here is that you don't synthesize from some abstract representation. You do look into a database, and that lookup and that concatenation, or that append function in Mozart, becomes so-called concatenative synthesis, because you take pieces from your database and you always add them to the piece, and that's how you compose. Maybe disappointing in some sense that the composition is basically query into a data set of patterns, but well, I mean, on the other hand, it's a very powerful technique. Okay, so yeah, without going into the details, without really explaining how it's done, because we'll talk about you know, the OMAX or the SOMAX, and then the variable Markov oracle or the factor oracle algorithm that kind of was the basis for these techniques. And you know, there'll be later on, because before that we want to cover, you know, the questions of just generating random processes, and then, you know, the Markov aspect of it, and seeing how we can maybe manually create such mappings and stuff like that. All right, so I think enough said about this. Let me go back to our lectures. Okay. So our next topic, well, we said we want to talk about probability, really, because there is that random aspect that drives the composition process. So I'll cover part of these slides today, and maybe go back to some musical motivations. But now we shift a little bit to talk about math, right? Probability. I will not get to information. We'll come back to these slides also next week, because it has, you know, several topics. So I want to define some notions of probability, statistics. I don't know how you know, redundant it will be to some of you. I'll try kind of to pace it relatively quickly, just to make sure that we have the basics covered. But if I'm going too fast, just let me know. So there is this notion of probability that kind of relates to experimental practices of not musical experiments, physical experiments. You do something, you know, there's something that happens in the real world. We call it an experiment, like tossing a coin, and you have certain set of outcomes that will be the sample space, and every event is basically a single sample from that sample space. So when you repeat the experiment, you get some possible combinations from the sample space, and then you look basically on how many times they happen, and you call it probability. Now here there is a little bit of a double meaning. One is the real probability of whatever the underlying process in nature. Another one is, you know, you're basically trying to learn these probabilities or estimate them from experiments. So one thing is counting them as you repeat to kind of see how it behaves, and one is, you know, the actual truth, or the basic, the ground truth that is beyond whatever happens in that physical space, which we really don't know, but we can either assume it or maybe learn it. But the probability of an event basically tells you that something happened. It's a positive number. If you're sure that something happens, like if you think about like something happened in the whole space of events, of course the probability will be 1. If you have a lot of small events, if they're disjoint or independent of each other, you sum the probabilities for each of the events if you want to know the probability for, you know, the sum of these events happening. And you can count them. So this is in some sense an estimate. There is a true probability, and there is so-called frequentist statistics. You count the number of times A happened, the n of A is the number of times A happened over all n, capital N experiments, and you'll call this your estimate of your probability, okay? Or the frequentist statistics. So there are random variables that can be continuous, that can be discrete, and if our variable is you know, gives you a numerical outcome, then you have a probability of x equals x. So, you know, given to say x equals, you know, the x is the random event, and the uppercase and the lowercase is the outcome. So for the random event to be coming up with X as an outcome, that gives you this probability, okay? And then if this is a continuous, then we have infinite, we cannot have infinite precision, so because we have infinite amount of possible values. So you kind of break it into chunks, and then you ask, well, what is the probability that some event will fall between A and B? And this will be basically summing all these probabilities. So just to distinguish between discrete probabilities and continuous probabilities. Yeah, you can ask all kinds of questions. Let's say if you have 3 rolls of a die, and you throw the dice and see what is the number that you come up with, the sum. So in case of the Mozart game, we had 2 dice, here we have 3. So what could be the probabilities? What's the probability of X equals 5 or X equals 10? We'll not solve it right now, but you can see that, you know, depending on the possibilities, you can have, you know, 1, 1, 1, you can have 1. You have all the permutations, you have maybe more possibilities to get, you know, combinations of small numbers. And then, you know, if you have, you know, the event 666, right? If you throw all 3 dice and 6, the 18 will maybe happen only once. So you can see that there is some kind of different possibilities of combinations that actually govern the statistics here. Now, usually in random num variables, we talk about the mean or the expectation, okay? So this is the empirical calculation of the mean. You basically take the values and you divide by n, you sum them, and that should be equal or equivalent to actually knowing the true probabilities, and this becomes basically the center of gravity, if you want to think about this, because probability is kind of how, you know, how the weights are distributed. You know, the higher probability, you think about this as being heavier on that specific value of X. So this is kind of the center of gravity of the probability distribution. That's why if you think about the Gaussian, you know, the mean is at the center, it's balanced. But this is how you can estimate them as empirical. In the continuous case, you replace the sum here with the integral. Now, one thing about, just because this is linear operations, so the mean of 2 different variables becomes the sum of the means. We're not immediately going to use any of these mathematical properties, but just have to make sure that we understand what they are. So if you have, again, 3 rolls of a dice with the sum, okay, so what is the mean? You can ask what it will be. Now, over many throws, what will be the average outcome of let's say, yeah, you can have an operation which is a sum, you can have a product, and for every, so X and here, one sum, one product is basically a new event. And then you can ask, what is the mean value of that function? Another one is how spread around, or what is the distribution around the variable. That'll be important if you think about processes like Gaussian processes, where basically the variance, the mean and the variance defines the whole distribution, okay? So variance is really, if this is the mean, E of X, expectation of X, sorry, this is the mean, okay? So this is the distance of, this is the spread of any outcome from the center of gravity. And this is Euclidean distance. So you can think about this basically of how spread that distribution is around the center point. Just using basic algebra, you can kind of open this expression in this way, and using also the sum property of the linear property of the expectation. If you follow this equation, you can see the variance is basically the expectation of X squared minus the E of X squared. Okay, this is kind of an easy shortcut, but I think the main meaning here is really the spread of all the outcomes of X relative to the center or the center of gravity in Euclidean sense. Okay, this is kind of the variance. This is, in Gaussian distributions, that's basically how wide would be that bell-shaped distribution. Again, I assume that you're familiar with this a little bit, because otherwise all my kind of hand waving doesn't make much sense. Now, Bernoulli distribution is a simple case where you have a binary variable. Outcomes can be 1 or 0, success or failure. So you can have probability of x equals some value p, and this kind of lowercase p. Of course, the other event is 1 minus p, so the other outcome. And then if you have many events that happen, okay, then basically you have p that repeats itself x times, or y minus p that repeats itself 1 minus x times. And this is kind of the expression for the probability for the Bernoulli distribution. So Bernoulli distribution, let's say flipping a coin. So if you flip a coin and you flip it 10 times, you have 3 heads and 7 tails, and the probability for heads is whatever that p is. So that'll be p to the power of 3 and 1 minus p to the power of 7. That's the probability for that specific sequence of events. In Bernoulli distributions, you can, we're not proving this, but you can show that the mean for a single event is p, okay, and the variance is p times 1 minus p. And what else? Binomial distribution is like the Bernoulli, but when you have multiple draws, okay. So because of all possible permutations, you add this factor of n over x, okay. And again, because you have n events, it's actually the example I gave before, where you have, let's say, 10 coin flips. It's the binomial distribution. The Bernoulli is just a single event. Yeah, I think the confusion is because here x can go from 1 to n, and here x was just a single event, whether it, p or 1 minus p, if x, let me just make sure that I'm not confusing you, because if x equals 1, right, then I mean, this in some sense, I think the confusion is because they use the same expression here, but this is just a shorthand for if x equals 1, then you have p. If x equals 0, then you have 1 minus p. So that's just a shorthand for this, okay, where x is either 1 or 0. Here x can have all of these, because you have n experiments, so that's how many times you have the zeros and ones. So the previous example actually applies here. This is the binomial distribution, basically repeating the coin flip n times. You can see the plots of such binomial distributions. Okay, so this becomes close, like it starts looking like a bell-shaped curve, which is typical for Gaussian distribution. And this bell-shaped curve is really shaped by this n over x permutations. So depending on the p itself, okay, all of these experiments are for 100 coin flips. Okay, that's what makes this shape. But the probability, the mean, is around p. So you can see that this is the mean here. P01 is the mean here. P025, the mean is here. So it'll be around 25 because it's times 100. And at 75, it should be here, and so on. So you see how the mean shifts it, but the spread around this is pretty much governed by the whole permutation aspect. Poisson distribution, okay, that's kind of a different way of thinking about events that happen according to this type of distribution. You can kind of derive this from binomial distribution. It is typical for some arrival events. We will not kind of dive into what exactly you know, what is exactly the processes that Poisson distribution describes better. It's different from the coin flip, but it also has these types of behaviors. You can see that, you know, kind of spreads out more as you change this parameter lambda, which is here. Okay, these are kind of the classical distributions, and then of course the Gaussian distribution, which has this expression here. Okay, so the shorthand is X is distributed as a normal distribution, and we use normal Gaussian in interchangeable ways with the mean mu and the variance sigma. So that'll be the center of gravity, that's the spread. And this is how it's explained. And that's how it's not explained, written out in mathematical terms. And this exponent of X minus mu squared divided by 2 sigma squared, that's the bell-shaped curve that we see when we talk about Gaussian distributions. I don't think I have a plot of it, but it looks very much like the binomial distribution. And if you want to think about some outcome of a Gaussian continuous variable falling in interval between A and B, that's how you calculate this. Okay. So again, mu is the mean, sigma square is the variance, and the nice thing about Gaussian distributions is really that a sum of Gaussian distributions is also Gaussian. So for this question, if somebody wants to solve it in your own time, you basically can, the means sum, the variances also have kind of a nice mathematical relations between them. So the sum of them becomes another Gaussian distribution with the new mean and new variance. Okay. Now, if you have more than one event, you talk about joint probabilities. So if you have events that are not independent but dependent, then you have to calculate the dependencies between A's and B's. In the case of, let's say, coin flips, usually the events are independent. Okay, so this is how it's expressed. Okay, okay, I'll have to fix the slides here. But if you have multiple events, okay, a set of events is independent if basically the probability of their joint occurrence is the probability of each one of them separately, just multiply them. But if the events become dependent, then we have basically another distribution with joints that governs their joint occurrence. And this will lead us to Bayes' rule that we'll use much later, but I would like enough to cover this today. This is the Bayes' rule. Basically tells you this notion of conditional probability. So if you have an event A that you know that happened, what is the probability that event B will happen? And again, for this to have any kind of practical meaning, that means that there is a dependence between the events, because if they're independent, then basically the probability of B given A is just probability of B. And you can see that this translates to the same equation here. Now probability of AB is the product, right? So for this not to be the trivial product, something has to be happening here. There is this notion of conditional independence. That's something that's used a lot in graph theories and also neural networks. You might have another event C that if that event is known what happens, then even if A and B are dependent between them, if you know, let's say, some kind of current relations of C that spawns like A and B, if you know C, maybe now A and B are independent, so that's conditional independence formula, okay? What else? Now, that conditional probability is also used to do inference or derive some conclusions about events, how one event changes our expectations or estimates of another event. So this is really just a definition, but now it becomes a Bayes rule. This is kind of a Bayesian formula, but it gives us an example of conditional probability. So if this is, an experiment or measurements that we do one is whether it's a rainy day, another one is grass wet. You can see that you have these combinations, wet and rain, wet and not rain, because maybe the sprinklers were working, not wet and rain. Very low probability, but still happens, and not wet and not rain, another probability. You can see that for every event like this, given an R, okay, and the W is sum to 1. So every column here sums to 1. Okay, these are basically the conditional probabilities, and you can have some prior probability just of rain happening or not, which is given independently of anything else. So 80% of the time you have rain. You can represent this information as some kind of dependency graph. Okay, and if rain causes the wet, this is kind of the causal relations, and you can go back and do the inference of what is the probability of rain given that you observe the grass. So if you observe the grass, you can try to infer how likely that it was raining, and you can use the base formula for that, and just some terminology. If we have a prior information about something, okay, and you have the probability of something happening given an event before, so this is called the likelihood, okay, and this is a posterior. So in many cases where you think about now something that drives another process, okay, let's say you have and we spoke about this random process or some query that happens that drives lookup in a table. You can think about this as learning some likelihood of the next event given the previous event, and you have some prior which generates your events. Okay, so this is in some sense the process to drive your generative part. You can also do the inference and see what, given the outcome, what was the cause. Okay, so this is the posterior and prior. I know that at this point, kind of these are just definitions. They don't make much sense in terms of, you know, things that we are going to right now, or the things that we're doing right now. But this idea of two events that have some kind of a statistical relation can be thought about some kind of a soft causal relations between them. And if you have, you know, that aspect of hypothesis and evidence. Okay, so this is kind of terminology that I would like to introduce. Okay, because here we said that, you know, you have something that causes something and then you can infer it back. Usually we formulate this as a hypothesis, okay, that it was kind of an underlying cause. And we see the outcome, which we call the evidence, okay? So then many times we talk about what is the probability of this evidence given the cause as information that passes from hypothesis to evidence. But if you want to go back and infer the hypothesis given the evidence, we call this inference, okay? So given the hypothesis and evidence, this is the terminology that is often used, that, you know, we assume that the prior on the hypothesis has some probability, so that hidden cause happens with some probability, that's the prior, and this is the, you know, the causality relation, which we call the likelihood of having some kind of a event given or evidence given the hypothesis, okay, and then we need to normalize this over the all possible evidence. And using the base formula, we can kind of use that to make the inference, basically saying, given the evidence now, let's say you made some experiments and you measure the evidence, you can try to infer the causes, the underlying causes. I think that's pretty much it. We'll talk about complexity later. So yeah, I felt we need to kind of to cover the basics of random variables and kind of the terminology and the basic notions of coin flips and maybe joint events. So before we take maybe we'll take another short break, because the last part is fun. We'll just watch some videos about music and how music, a musician use probabilities, okay, and then also, well, I mean, there's going to be some reference to looping techniques, okay, to actually compose music, because I think, beyond the math and some little bit of kind of small, I wouldn't call it synthetic, but limited examples that we do in homework, kind of seeing the larger picture. That's part of the discussion that I think definitely is of interest to those who are going to use these algorithms for creation. So seeing the historical perspective. But very briefly, let me see if I have, let me find the examples. Quick notebook here. Just a sec. Okay. So this is a small notebook example talking about NumPy, which is one of the standard libraries. You have used it already, I believe. So it has NumPy has a random object, or a set of functions under NumPy that allow you to generate different distributions. Okay, there's also a random, let me kind of skip down. There's also random native in Python. Okay, it has slightly other methods that are implemented under this class. So if you see sometimes random as NumPy or random without NumPy, just know that these are slightly different libraries that need to be imported to use them. So if you look at the NumPy, so we import NumPy as NP, and NumPy, any random process can be seeded, basically, because these are not really random processes. There is some kind of algorithm that generates these random numbers. But if you set a seed and you repeat the same code again, you'll get the same random outcome. Okay, so if you want to use a random seed, because you want to debug a process, or you just want to make sure that even if it's a random process, for some purpose, you want to repeat the same process again without that randomness, so the sequence of random events will repeat itself, then you should initialize a seed. So for instance, in the NumPy normal, of course you can type help and seed. It's mean, variance, and the dimensions. Okay, so if you run this code here, of course, every time you will run it, you'll get to just import this. So every time you run it, you'll get slightly different outcome. Okay, but if you repeat this experiment enough times, you'll see that this will be in the mean around 1, and the variance will be also 1, and it's always two-dimensional. So you have two samples. Okay, you can also have a whole matrix of 3 by 2 generated. So this is again mean 2, variance 1, the dimensions. Okay, or if you just provide, so this is normal. If you want to have 3 random, rand gives, okay, let me just make sure I'm not confusing anyone. Okay, so help. So normal is normal. And this is, okay, method, okay. Create an array of the given shape and probably with random samples from the uniform, right? So this was Gaussian, okay, normal is Gaussian, and round is uniform distribution. So uniform means that you basically have equal probability for any number between 0 and 1. Okay, so in this case, we generate 3 numbers. Okay, if you run this again, you'll get a slightly different set of 3 numbers. Again, you can have a uniform distribution as, in this case, because it's uniform, doesn't have mean or variance, it's already fixed. between 0 and 1 uniform distribution. So by providing here the numbers, you shouldn't confuse. So, every function has its own arguments, right? So we said mean, variance, and dimension. Here it's only dimension. Okay, so you have 3 by 2 by 4. So this is a tensor officially because it's, we have 2 by 4. Okay, so you have 2 by 4, and you have 3 of them. So this is 3 by 2 by 4. Okay, well, tensor, yeah. So not the structure. I mean, implemented as a structure, but still, I mean, think about this mathematically as a tensor. Here, this is round n, this is normal. You have again slightly. You basically have the same function with different calls, so they have different parameters. Normal, you said mean and variance. If you use this round n, that assumes a Gaussian variable with 0 mean and unit variance, okay? And because this is very useful, maybe you don't want to specify the mean and variance, you're using the usual 0, 1, mean 0, variance 1. So for this round n, the 6 is only the number of samples that you can use, okay? And again, if you round n, these parameters will be the dimension of the tensors that you create. Now, if you have a list of outcomes, it could be numbers, it could be any kind of a list here. A random choice will basically select one of these entries. Okay, you can put letters here if you wish. Okay. And now, if you have a random choice and the size, you can actually make these choices and put them into a matrix. Okay, so basically, make a 2 by 3 matrix with every time making a random choice of one of these entries. Okay. What else? So that's basically the same thing. You can specify, yeah, that's now if you don't specify here, the sequence of values, but you use just one number, this is treated as a range, which means what is range? It's from 0 to 3. Okay, so instead of writing here 0, 1, 2, 3, you can put a 4. Okay, and it'll create numbers between 0 and 3. Okay. Now, yeah, I mean, like you have sort of like to look it up in the help in the documentations for each library to know exactly what they're doing. So this is why I kind of summarize. It's not super interesting, but just kind of to give you an overview. Uniform distribution, again, limited in 2 and 10. You can have a size. Binomial distribution that we mentioned with the probability P and the number of experiments. Okay, you can also repeat this with different size. Okay, so it was just by chance that we had the same number. These are basically two separate independent experiments. Okay, you can have 2 by 3 experiments done here for this binomial distribution. You have Poisson here, as you can sample them. You can sample them 4 times and get these numbers. You can sample them into a matrix. Now, round int, you get the random integer to 150. Let me just make sure again. That I'm not confusing you, because yeah, you're gonna have to look up the exact definitions of these method. Okay, return random integers, okay, from discrete uniform distribution at a specific time between low and high. If high is none, then the results from 0 to low. So let's see what we had here. Yeah, so yeah, you'll get a number of about 50. Okay, sample. Okay, let's do the same trick again and make sure we know what's help. And be random sample. Random sample, see random sample, they can do the okay. This is not for random sample. Okay. No, what did I do? See random sample. I do that. Sorry. Okay. So okay, if anybody has a quick advice why I'm not getting to the right help, let me know. But anyway, if I'm not mistaken, this is just giving you a sample between 0 and 1. Okay, and so let's assume that's what it is. Please verify. You can get this in 2 dimensions, 2 by 4. You can choose again random integers between 0 and 9. So there's a lot of redundancies in these functions. If you use the native random, not the NumPy, you have again random for a range of numbers. It'll be from 0 to 19. Okay, so every time you run it, we'll get a different number in that range. You can have a range between 2 and 20. Okay, so you'll get basically from 2 to 19 here. For instance, here, okay, you get random numbers between 1,999. So you'll get basically 4 digits random number every time. Okay, I have to print it to see it. And this is 2 numbers. Okay, so you have round range here. So you have between 1,000 and 10,000 here. Yeah, I don't know what else. We can actually create now a sequence of these events. Okay. So what we do is, okay, we take some index, okay, in range 1,000 means we'll have from 0 to 9,999 events, and for every event here we'll sample this as a random range of 10, so it's 0 to 9, and we'll create a sequence. So this is one way to create a sequence of random samples that are independent, but you can set basically the range of values here from 0 to 9. Okay, now let's move on a little bit to processes. The basic type of process is so-called Brownian motion. Now, Brownian motion is a random walk. Okay, and what the random walk does basically takes a small increment, okay, and moves up and down by this step y. Okay, now actually I took this sample from this from this article was data science, so I will throw in this this notebook to the slides folder, so you can kind of go through that. But the whole idea is that you have a baseline. So in this case, the baseline here is this value x0. Okay, so you basically have a set of constant values, and then from that reference point, you move up or down with the step size yi. Okay, so yi is a random choice. You either go up or down. So 1 is going up, -1 going down. And you have also this normalization factor depending on the number of steps. And what you do, you move up, that becomes your second step. Then you sum them together, so you're already in the second point, and then you move up and down from that point and so on. So you basically get kind of a run, like a drunken walk or drifting process, okay, that creates this random walk, okay. You can do this either by random choice of 1 or -1, or you can do your choice of steps from a normal distribution, okay. So if we run this step, So if we do these steps many times, okay, we get these types of, okay, here like 4 times we try these processes, okay? So each one, you see, it's kind of a drift process that goes up and down. And there are a lot of physical phenomena that these things can describe. Some of them are like stock market behaviors, a slightly different model, but still, I mean, the drift process happens in some kind of exponent of a different function. But you also, if you remember the previous talk about random walks on Riemannian spaces, there was some kind of a drift process. There was some kind of a random walk that happens here. Here, basically, the random walk is really taking the previous step and going up and down, either 1 - 1 or Gaussian distribution. We'll also see how this can be done going through some kind of a walk on the network or walk on the Markov transition matrix. Okay. Now, if you want to see this in 2 dimensions, basically here we have 2 Brownian motions. Okay, we just plot one as x and one as another one as y, and so they're kind of independent. But it's nice to see because now you have a 2-dimensional random walk, one on this axis, one on that axis. If we had a 3-dimensional plot, you can see basically some kind of a random drunken walk on 3 dimensions. So these are really the basic tools of just creating these random choices with some kind of a time structure in the case of Brownian motion. Next week, we'll also cover other processes or other ways of inducing dependencies in time. Okay, so this whole idea of having some kind of smooth process in time is, and this is kind of an important thing to keep in mind. One is the choice of every single event, okay? And then also how the previous choice influences or how it kind of biases or what is the joint distribution. That's where that theory of having A and B, not independent events, but having some kind of a dependency, that's where it comes in. So if you want some kind of a smooth motion, okay, in 1 or 2 dimensions, relative to this, which is really in the set of independent samples, okay? So we'll call this one later. We'll talk about this kind of white noise, and this is, some people call it brown noise, but it's because it's brown in motion. So it's not brown in it. But these will be things that we'll talk about a little bit more in the following classes. So that kind of summarizes pretty much what I had in mind for the theory of just generating random numbers and random processes, or at least the introduction to that. So let's take a very short break because I have few historical videos that I want to share that will give a little bit more of a musical or artistic context to what we do. So let's meet at now it's 33. Let's meet at 40, and then we'll have about 20 minutes to look into some of these other videos. So let's make like a 7-minute break, and we'll meet again just for the last conclusion. Now, I know that I not promised. I'm happy to go into discussions and questions instead of me showing the next set of slides. But unless you have any requests, so the last 20 minutes we'll see this one of more of the historical videos, and I'll kind of walk you through some additional slides, and of course we'll also continue next week, but we still have some time. So let's meet in 6 minutes, okay? And then see, we can either talk about anything that you would like, or we can start watching this kind of more of the musical context and musical historical videos about using randomness, and actually a lot of this talks about also looping techniques. Right, so I'll see you pretty soon. Okay, I'm stopping the recording and then I'm pausing it, and See you soon. Okay, so yeah, I think I resumed the recording. So we'll continue just for the last few minutes with these slides. Let me make sure that I'm sharing the screen. So next set of slides that I actually put also in the lecture notes is called aleatoric music. Let me see. Yeah, so that should be, yeah, this one. Well, we'll have just to see the first video, which I think is, is a worthwhile and also fun way to kind of define what, why musicians are looking at these processes, what kind of experimental things, experimental in the sense of musical experimentation, musical styles, what it allows them to do. And also at a certain point, I'll be happy to kind of to dive into the question of, a lot of machine learning now is actually trying to use also, I would say, aleatoric methods for composing music in a traditional way. So there's kind of becoming, I won't say full circle, I don't know what to call it, but we're coming in some sense back to the idea that we are modeling a lot of traditional things that we describe as grammars or some formal techniques that we'll be also talking in the future lectures, but now we think about them in statistical ways. So they also become in some sense aleatoric practices, but in historical sense and also in terms of the musical drive, the exploration of new musical methods, aleatoric music plays an important role. So let's watch this video, and if time allows, we can also chat about this either today or next class. So here is, a fun video by, oops, sorry.
Let's talk about what happens when you combine two different musical creation techniques.
Sorry, okay. Yeah, so yeah, let's go back and restart this video.
Let's talk about what happens when you combine two different musical creation techniques. The use of looping, which is the repeating of a portion of sound over and over again, and the use of chance, which is allowing music to be affected by an element of unpredictability or randomness. When combined, the results can be incredible, forming the most well-known technique in what we call aleatoric music. Today, aleatoric technique can be found everywhere, especially in electronic, rock or ambient music, and it can be traced back to composers writing in the early to mid 20th century, yet another illustration of how amazing that period was for music. And what's more, it's often used very effectively in game design too. So in this video, we're going to be looking at how it's used across these different genres and how much there is to learn by investigating its history. Now, we've all seen solo performers using looping pedals to create multi-layered backing tracks using just their voice, which is pretty enjoyable to watch being done live, with probably my favourite example being this TED Talk by Beardy Man. Or there are those who play live sets using multiple pieces of linked up hardware where the looping is a little bit more malleable, like this work by the YouTuber Michael Forrest. Generally speaking, this is one of the two major variations of looping technique, where everything is synchronized to a steady rhythm. The other major variation of looping technique is where the artist avoids syncing to any type of beat, often for the purpose of creating free-flowing ambience or background texture. Here's a fantastic example by the YouTuber Aleatoric, who creates his own looping devices out of cassette players. And with each looping device running at different lengths, new combinations of sound will just keep developing over time. I highly recommend checking out both Amulet's and Michael Forrest's channels, and I've put relevant links below in the description. We'll come back to the idea of using looping for textural purposes in just a second. Now, when sticking to a strict tempo, one simple trick is to deliberately lengthen or shorten the number of beats in any given loop to achieve more complex syncopated patterns. For a quick example, let's just jump into Reason to see what I mean. First off, I created a simple pattern in 4-time. Now let's add a pattern that loops every 3 beats, and we'll first play it slowly so you can hear the rhythmic offsets that are being created. And on top, let's add a pattern that loops every 9 beats, and we'll also play that slowly. Now if we quadruple the speed of both these patterns, we can hear how nicely they bounce off each other. Now one interesting feature of this particular device, where we begin to transition into a discussion about aleatoric music, is this button, called random, which allows the order of individual beats to be left up to chance. And this simple combination of controlled chance and looping can be traced back to 2 composers during the mid-20th century, Alan Hovhannes and Witold Lutosławski, who independently of each other came up with a nearly identical system. To understand what they were trying to achieve, let's look at a common problem faced by composers. Let's say you wanted to achieve a detailed texture like this example from Hovhannes' Magnificat. Or this one from Lutosławski's Piano Concerto. Well, if you were trying to use traditional notation, let me just lay out the notes from Lutosławski's score here. You'd first want to avoid having all the notes synced up like this. That just obviously doesn't sound right at all. So to get close to what Lutosławski achieved, you'd need to create all kinds of complicated offbeat patterns and tuplets. But, as any composer who's put something like this in front of an orchestra knows, performers and conductors hate this kind of thing. It's ludicrously hard for the musicians to time it properly, and the conductor won't be able to micromanage this level of rhythmic complexity either. The only way this could work would be to devote an impractical amount of rehearsal time. And with classical ensembles, where you'd be lucky to get even 3 rehearsals, that's not going to happen. Moreover, it would be difficult to predict the outcome ahead of time, and poor performances would be much more likely to happen. And for those of you thinking, well, I suppose those very few of you thinking, have you never heard of new complexity? I have, but that's a different discussion for another day. And so Hovhannes and Lutosławski both conceived of almost identical solutions to achieve the sort of complex flowing textures that they were after. These techniques are pretty easy to describe. If we stick with Lutosławski's Piano Concerto for a second, let's focus in on one instrument to understand what he's doing. Now at this point, a performer would be reading the notation as normal until they reach a section that looks like this. A few notes sandwiched between 2 repeat bars. This is our looping mechanism. The musician now knows that they must repeat this loop over and over again until the conductor gives the signal to stop, at which point the musician abandons the loop immediately. The conductor's cues are often notated like this. But what's really liberating about these loops is that the performer is no longer tied to the meter, so they needn't worry about staying in time with everyone else. These loops are often coupled with the direction ad lib, which in this context indicates that the player can improvise certain aspects of the performance, things like articulation, volume, or even the ordering of the notes sometimes. All in all, this system allows the composer to achieve new sounds by actually relinquishing control over certain elements of the performance, a sort of controlled use of chance that opens up all kinds of textures and orchestral colours that are hard to achieve any other way. In his Piano Concerto, Lutosławski uses this technique to allow the pianist a high degree of rhythmic flexibility, so that every little phrase has room to breathe. I've animated an example I particularly like in the opening, where 3 flutes jump between different loops to provide a background texture for the pianist to play over. And what's interesting here is how all 4 musicians are able to work together despite being rhythmically independent from each other. I've used this technique in my own music too. In this example, I'm giving 3 string players rhythmically independent looping patterns, which allows a guitar player time to play a solo as he sees fit. Another classic variation of this idea can be seen in Penderecki's Threnody for the Victims of Hiroshima, which has been fully animated on this channel, Gerobach, which I highly recommend you watch. Each of these strange symbols represents a different unconventional way that a player can strike their instrument, which, along with loosely coordinated looping, creates a sense of pure mayhem. Today, composers are still modifying this technique to suit their own style. Take the composer Gregor Forbes, who studied with me at the Royal Conservatoire of Scotland. His aleatoric techniques are sometimes quite open-ended, allowing performers to take control over larger things like length and overall structure. Take as an example his piece Colour Fields, written for 3 players, clarinet, violin and piano, where each player is given only 3 very short fragments of music to choose from. Here you can see the 3 options available to the clarinetist. Now, not only can the players choose which fragment they want to play at any given moment, they also don't need to play the notation from left to right. And when you think about it, aleatoric technique is actually perfect for game design too, where the chance events are provided by actions the players are taking, which then affects what the music is doing. Take the game Flower for example. In the opening, the background music loops around the key of D. It's quite simple to begin with, until the player begins to interact with the scene, which triggers chords and musical flourishes that are harmonically consonant with that key. Notice also that the lack of a strict rhythm is helping these moments blend together nicely. Here's that same technique again, used in the game Flow. Both of these feel quite similar to the techniques employed in Terry Riley's famous piece In C, which, as the name implies, strictly locks down the key so that other asynchronous rhythmic choices can be made, without the result sounding messy. And then there are games that want strong driving beats in their music. The most common aleatoric technique that they use is to first create a library of multiple synchronized loops, and we'll look at the game Luminesce for an example of this. Initially you can hear an underlying pattern that starts off quite simply. Then, as the level gets harder, to ramp up the feeling of progression, additional layers of percussion and harmony are triggered by the actions the player takes. Then there are also moments where the music is stripped back to just one layer to indicate that a new level is about to begin. I like this because not only does it give you a bit of breathing space to prepare for the next level, it also sort of clears the air for the music so that it can change pace or maybe change the key. And I hope you also noticed how all the moment-to-moment effects and explosions have been tuned to complement the key. Another common game technique that really makes it a pleasure to listen to. So that's my quite quick introduction to aleatoric music, which just keeps on morphing and changing through the decades, with different musicians arriving at it from completely different angles. If you're a composer, it's a very nice way to include a degree of looseness into quite rigid musical structures, and I highly recommend you give it a try. In fact, if there are any people out there who have come up with their own novel versions of this technique, no matter the genre, just let me know, and if I get enough responses, I'll do a follow-up video to feature them and discuss their individual working methods. Like, you could do something really revolutionary, like this. Let's take a random 2-syllable word, like this one. Subscribe. And a long 3-syllable phrase, like this one. Ring the bell. And yeah, that's good. Let's play that. Ring subscribe. The bell. Subscribe. Ring the bell. Subscribe. Ring. And now, to introduce an element of chance, that's where you guys come in. The actions taken by you, the viewer. It's a great illustration of, the kind of novel internet composition, because we're all connected and we're democratizing the listening process and
little, humor. We ran a little bit over time, so we'll end at this point. I think there's a lot of potential here to discuss, really, randomness, use of randomness, whether this is to imitate existing styles, and maintain and basically creativity within a framework, or go outside of framework and explore these textures, ambient music, complexity. I mean, there's a lot going on here, which uses maybe a lot of these statistical techniques, as well as structures that are being driven by these techniques. So that's kind of the underlying maybe common ground here. I think a lot of relations to the Mozart dice game could be drawn here, but we will not kind of force this discussion too much, unless we kind of want to explore specific aspects. So anything from textures and novel music, ambient music, atmospheric music, games, or imitating existing styles and creating new music within a very tight framework. I mean, there are different challenges, but I think we'll try to explore at least some of them, either techniques or by discussing this more from the artistic, philosophical perspective, as you wish. So thank you for your attention, and yeah, good luck with the homework. We'll see you next week, and feel free to get more discussions going on Canvas or email me. All right, so thank you. And the random Python notebook, I'll drop it. I'll drop it in the class, in the lecture slides.
By the way,
Yeah.
professors, so
Yeah.
I wonder for next week's lecture, are we going to do that in person or still online?
I will be back, so we can do this in person. I mean, yeah. I mean, I
Right,
hope to see.
cool.
I
Definitely
think
in person.
Yeah. I think I prefer it in person too. So yeah, we'll meet next week, and also I'll send a message also to make sure that everybody knows. Okay. Well, see you. Okay. Thank you. Bye bye.